Hey guys, heard you're learning about quadratic functions. Have fun.
Okay, let's start by defining a quadratic function, even though we probably know lots about it already. So we are going to let a, b, and c be real numbers. Where a does not equal 0. Then we'll have f of x equals ax squared plus bx plus c is a quadratic function. Okay, so just something I want you to think about. Why is it so important that we define that a cannot equal 0? Something to think about there. Another thing that I just want to point out is that we know that the degree of a quadratic function is always going to be 2. It's important. If the degree is not 2, then it's not a quadratic, right? And we also know the type of shape of graph that this forms. It would be a parabola. Okay. So currently this quadratic function is in what we like to call true standard form, right? Standard form of a polynomial function, because this is a polynomial like we just talked about. But we also have what's called vertex form. Sometimes we call it standard form, but that can get kind of confusing because we have standard form for polynomial. So we'll just really refer to this as vertex form. We have f of x equals, we'll talk about what all these mean in just a second. A times the quantity of x minus h squared plus k. Okay, now because this is called vertex form, of course, this tells us what the vertex is. The vertex would be hk, that ordered pair. Okay, which is helpful for telling us if we have a min or a max, which kind of leads me to my next thing. How do we know if it's a min or a max? Depends on what this a would be. So a will tell me if I have a vertical stretch or shrink. And A, depending on if it were positive or negative, would also tell me if there's going to be some kind of reflection of the graph, which is why I was kind of hinting at is how A can tell us if this will be. Something else to keep in mind is that H really would tell us if we're going to have a horizontal shift. You know, are we going left or right H units? And of course, K then, will tell us if we're having some kind of vertical shift. You know, am I going up or down K units? So let's apply this to an example. It says here, find the vertex and intercepts. So we're given this function f of x in standard form, right? We want to put this into vertex form. We find the actual vertex of this, and also we want to find the intercepts. And then we're going to make just a rough sketch of the function. It doesn't have to be perfect or anything like that. So go ahead and put me on pause. See if you can get started on putting this into vertex form. If you're really not sure where to start, I'll in a few seconds have just kind of the start to this to kind of help us out. Okay, so if you are looking for a hint as to where to start this problem, here's just kind of my first step here. And I'm trying to remind you that you do need to complete the square. So I started by bringing my constant over to the left-hand side. Okay, I factored out, you know, this 2 from the 2x squared and the 4x. So I factored out the 2 because I want this lead coefficient to be a 1 in front of the x squared. And in this blank, remember I have to do b divided by 2 squared. That's what's going to go in the blank. So when I do that, I'm going to have 2 divided by 2 squared, which is going to be 1. And what I add over here, because if I add one side, I have to do to the other. But don't forget, technically, if I distribute this 2, technically I did add a 2 to the right-hand side. So I'm going to add a 2 to the left-hand side. Okay, so if you needed that little hint to get started on this problem, go ahead and put me on pause again and try to keep working it out on your own. If you were able to do this on your own or you're just kind of ready to check, let's go ahead and check it. Okay, so in terms of putting this into vertex form, notice that I combine like terms to get the 9, and I factor this right-hand side. That was the whole point of completing the square. My last step was to bring this positive 9 back over here. So this is my vertex form, which allows me to identify my vertex. We were also asked to find the intercepts. That would mean both x and y. So starting with the x-intercepts, that's going to really require the most work here. Let's see if I can scroll this down. There we go. So I would set this function equal to 0, right? Also another thing just to point out is that you could use your quadratic formula. I think it's a little bit easier just to do this. So I have my 0 here. I'm going to try to isolate the x. So add 9, divide by 2, square root both sides. Notice that I get x equals -1 plus or minus 3 over root 2. Now notice that this current form isn't rationalized. I would guess that you have spent time rationalizing the denominator before. It's not necessarily important for upper level math. Like it's not something that you're going to be required to do. But I would suggest knowing it just for the sake of identifying two things that are the same. So for example, you get this answer, but you see the answer written in a different form. It's just nice for you to know that they are the same number. So to actually answer the question, we have the vertex at -1, -9. I had 2 x-intercepts. Now these I didn't rationalize just so you guys could see it. And my y-intercept is at 0, -7. And how do I get that? Well, first of all, I would plug in 0 for x in any of my forms. Or if I go to my standard form all the way at the top here, I always know that what my y-intercept is that constant in standard form. Okay, so just a shortcut to finding the vertex or the min or the maximum, there is a nice shortcut. We know that if we can convert it to vertex form, HK would be my vertex. But if it is in the standard form, like this doesn't really look fun to convert to vertex form using complete square. So if I do have it in this form, I could also find my vertex in this way. The x value of my vertex would be the opposite of b over 2a. The y value of my vertex would be f of the opposite of b over 2a. And there is a nice proof to this, so I'm going to go ahead and show you that. There's actually 2 of them. So I'm going to show my work and kind of briefly explain this. And you guys don't have to write this down, but it's just nice for you to know. So let's just take a look at this first proof. I'm starting with this quadratic function in standard form. I'm going through the process of converting it to vertex form. And notice that I'm just leaving it in this vertex form with a, b, and c. So I brought the c over. I factored out the a because I do want this lead coefficient for the x squared to be 1, which would make this b over ax. Then to complete the square, notice that this would be b divided by, the b term, which is b over a, divided by 2 squared, which is b over 2a quantity squared. B over 2a quantity squared, but also multiplied by a. Sorry, that's sloppy. That's filled in this next step anyway. And then I factor this right-hand side. So notice for my vertex, I have my h and then my k value. It would honestly be whatever I get when I input this. And the reason why, we said up top here that it's the opposite of b over 2a is because think about vertex form. This is a plus b over 2a, so that's why it becomes the opposite. A second proof here, just real quick, I could start with this in vertex form, and then if I multiply this all the way out, this is what I would get, right? If I multiply x minus h squared, then distribute the a. So the a would represent my a term, the 2ah would represent b, really the negative, and then this h squared plus k would represent my c term. So if I take the b part and I set b equal to negative 2ah and solve for hk, right, vertex form, I would get the opposite of b over 2a. Those are just two real quick proofs just to show why this would work. So what I'd like you to do without converting this to vertex form is I'd like you to state the vertex of this function f of x using this idea. Go ahead. Okay, just to quickly check our answer here, you should have gotten positive 27 over 2, comma, negative 221 over 2. Last example here says the textile manufacturer has daily production costs of C equals blah, blah, blah. Notice that this is a quadratic function. Currently, it's not written in standard form of a polynomial just because it's not in descending order. It's kind of in ascending order. So C is the total cost, and X is the number of units produced. How many units should be produced each day to yield a minimum cost? So remember, we're trying to determine the minimum, which in other words, we're trying to determine what's the vertex of this function. So here's an example of why, this idea right here could be useful. Instead of converting this quadratic into vertex form, like, I don't know that would be that much fun. It would be way more fun just to use that idea. So I know that the h value of my vertex is going to be the opposite of b. So 110 all over 2a. Okay, so if you did that, you should be able to simplify that, and don't forget what we are asked to solve for, how many units should be produced. So it would be this h value, so I'm going to let you guys go ahead and figure out what that is. All right, just a quick check. There wasn't too much more for you to do. If I do simplify this, I get that it's about 1,222. I did go ahead and find the k value of my vertex, or the y value, but I mean, it wasn't really necessary to know. It just asked how many units should be produced. So to answer this question in words, 1,220 units should be produced each day to yield minimum costs. If they had asked me what is the minimum cost, my answer would have been the k value. All right, so we talked a lot about standard form or vertex form of a quadratic function, how we can find hk. We can use complete the square to convert from that standard form to vertex form. And then also there is a vertex shortcut, which is pretty nice, that h is equal to the opposite of b over 2a.